Exponents and logarithms are only fun if you make equations out of them. So at the top of the page here is a logarithmic equation. And what this equation's doing is putting an unknown in the spot where the exponent that you're trying to focus on sits. Remember how logarithms work. This expression right here is saying, hey, we started with a base of 17. We put an exponent on that 17, and the result we got was 4,913. What was that exponent? Well, at the moment, the exponent is unknown, and so we put an unknown in there. The exponential form of this expression is to reflect the same process in a different arrangement. So this logarithmic form emphasizes the exponent, the x. Base of 17, result of 4913. The exponent was x. And here it's the same information. There's the base of 17, there's the exponent of x, and there's the result of 4913. Now, what is x? I don't know. We could go ask a calculator or do some trial and error or something, but that's not the point right now. The point is to be able to go back and forth. Okay? So here's an example where we're starting with something in an exponential expression, and we're going to put it in logarithmic form. Now, side note here, h is a constant. H is an unknown. E is a constant. Well, what the heck is E? If you haven't seen it before, go look it up. I don't want to get diverted into that right now. Here's the quick story. We've got some very common bases that we use for exponents. It's very common to raise 10 to a power, and its corresponding logarithm is log base 10. It's very common to use 2 as a power, 2 squared, 2 cubed, and so log base 2 is its partner. And there's what's called a transcendental number e. It's one of those very special numbers like pi that shows up all over the place. It happens to be 2.718, blah, blah, blah. And its logarithm is called the natural log. It's log base e. And in fact, it's so special that we shorten it to ln for natural log. So e's partner logarithm is log base e, or more abbreviated natural log. So here we have a base of e. We raised it to an exponent of negative 3.5, and we got back this other value h. In logarithmic form, we could write that we had a logarithm, or we had an expression with a base of e. We got a result of h. What was the exponent that made that happen? Well, it's the negative 3.5. And if we would like to use natural log notation, it would look like this. Okay, so again, we don't know what h is, but there's two different ways to describe the relationship between e and h and negative 3.5. One of the reasons exponential and logarithmic functions or expressions come hand in hand is because they are inverse pairs, just like x squared and square root. If you want to get rid of one, you apply the other. Here's an example of how that happens. Let's see if we can decrypt this expression. Natural log is log base e, right? So we could write this as log base e of e to the 2x minus 1 if we wanted to. Think about what this structure says. It says, hey, we had a base, and that base was e. We threw an exponent on e, and we ended up with e raised to the 2x minus 1. Well, what was the exponent that we put on e to make e to the 2x minus 1? Well, that's it's so obvious, it's difficult, right? It's actually 2x minus 1. And so look what happened. We took log base e, or natural log, and applied it to the exponential function, and we reduced to 2x minus 1. In other words, the natural log and the e kind of eliminated each other, and this exponent just dropped down all by itself. This comes in handy when we need to solve equations, and it works backwards too. E raised to the natural log of x squared is equal to x squared. So remember, if you have an equation with e or any other base in it, and you want to drop the exponent out, perhaps to solve for a variable, apply the corresponding logarithm, and vice versa.